Hello, my name is Shahab Dean Mohageg. I'm the director of West Virginia University Laboratory for Engineering Application of Data Science, WVU Leeds. I will be talking about shale analytics today. This is an introduction to the technology in order to provide you some insight on what you can expect to be exposed to during rest of this presentation and rest of the course. Uh, what I'm going to cover is an introduction to this technology as we move forward. As you know, this technology is all about data. And without data, you're just another person with an opinion. And this is mentioned by Deming in early 1990s. And it had, of course, nothing to do with shale, but you hardly find any other places that this particular statement is as correct and deeply involved with as it is with shale. This has to do with the fact that engineers and scientists that are involved in the day-to-day operations of uh, shale wells, they develop an intuition that requires to make the best of what is available to them in order to increase the efficiency and the recovery from the shale wells. However, full understanding of the physics and the mechanics of the storage and the transport phenomenon and the production operation of the shale remains to be quite elusive, and we have very little detailed scientific understanding of what is happening in shale. Because if we did, then we could have build a physics-based model of that. And the reason we're not there yet is, again, has to do with our lack of detailed understanding of the science behind the physics and the mechanics of the storage and transport phenomenon in shale. There are many opinions and speculations on what exactly happens when we embark upon drilling, completion, and hydraulic fracturing of the production in the shale wells. Much of the opinions and speculations have hardly ever been supported by facts and data. And in the occasion that they are, it's hardly ever transcends the fact that these are anecdotal evidences that have been heard or observed from here and there. As an industry, the fact is that we collect an incredible amount of data uh, when we operate shale wells. These data, which are field measurements and facts, it is hard to imagine that they do not have enough uh, uh, essence in them, enough information, these field measurements, these facts, and these data that can be used in order to generate knowledge that we need in order to optimize production and maximize our recovery from this very, very prolific hydrocarbon resource. It took our industry professionals many years to come to this inevitable conclusion that our conventional methods and conventional modeling techniques, they cannot substitute our lack of understanding of the physics and the mechanics of the completion and the production from shale wells. What these current conventional technologies that are used extensively for shale are these three technologies: decline curve analysis, rate transient analysis, and numerical reservoir simulation. There's a whole module in this course that we will spend some time to cover each one of these technologies to a certain extent. Let's talk about these traditional modeling that we do. Decline curve analysis, which is really not, a decline curve analysis is really not a modeling technology. It's a curve fitting simplistic process. So, but mainly we're going to talk about RTA, rate transient analysis, and numerical reservoir simulation, since they are actually technologies that are used for modeling. Shale as a hydrocarbon resource is a revolutionary idea that has now become a reality. The technology that has realized this revolution is innovative and quite game changing. However, as an industry, we are still using old conventional technologies in terms of modeling, scientific technologies to try to analyze, model, and optimize production and recovery from shale. In other words, when a lot of things happened and changed the way we handle reservoirs in order to produce hydrocarbon, those changes that took place allowed us to make hydrocarbon production uh, from shale. However, what didn't change is the science and the modeling technology that we have been using for the past more than half a century for modeling, optimization, and analysis of hydrocarbon production from the reservoir. So although the technology changed in order to make it possible to produce hydrocarbon from shale, our science and modeling technology did not change. We're still using the same conventional techniques in order to model and analyze and try to optimize unconventional resources. Our analyses and modeling efforts up to now have had quite limited success. Many engineers and managers in the industry now openly admit that the numerical reservoir simulation and ray transient analysis add very little value to their operation. Actually, you can tell right now in how little these technologies can contribute simply by identifying several large companies in the United States that unfortunately had to get rid of their entire reservoir engineering community in their company and lay them off and get rid of them simply because the management come to the conclusion this is the fact that they have gotten rid of these parts of their company, the reservoir engineering part. That's a fact. However, it seems to me that the reason for it is they did that to the reservoir engineers, not to production and completion engineers or to geologists. To a large extent, it has to do with the fact that maybe they have come to the conclusion that what the technology that these traditional reservoir engineers have been using, which is ray transient analysis and numerical reservoir simulation, has hardly added anything to these companies' production and recovery of hydrocarbon from shale. This could have been foreseen based on the essence of these technologies and how they model the network of natural fracture uh, that is the main issue in the production of hydrocarbon from shale and induced hydraulic fracturing and the way these two are coupled and interact with each other to make hydrocarbon production possible from a shale well. Conventional technologies are too simplistic and are not capable of realistically model the physics of the production from shale. Of course, the physics, as much of it as we understand today by dealing with it. They make unreasonable simplifying assumptions to such a degree that makes this whole process quite irrelevant. I will be talking about that a lot as we move forward in this course. Uh, in the absence of any other widely acceptable technology, of course, prior to AI and machine learning and its use in shale analytics and petroleum data analytics in this context, uh, since they have not, prior to this technology, since there was nothing else to be an alternative to the modeling of storage and transport phenomena in shale, then conventional technologies flourished in the past several years. So we're going back to mid 2000, 2007, 2008, all the way to almost more than a decade. These technologies were developed decades ago, more than half a century ago, And when all our oil and gas production were coming from trap rocks, from sandstone, from carbonates, and not from the source rock, such as shale. At best, these technologies were adapted to be used for carbonate formations, and in some cases for cobalt methane formations. The fact that these technologies do not work when it comes to shale has become self-evident simply because they have not been able to actually contribute to optimization. This has to do with the fact that these technologies can be used to support and mathematically show any idea and opinions about completion design and production outcome from shale wells. Uh, since these technologies are all about assumptions and simplifications, no matter what is your opinion or your boss and manager's opinion and ideas, uh, they could be completely different from one another. Nevertheless, they can make them look pretty correct because there are so many assumptions and simplifications in these models. Therefore, no matter what your manager wants you to or to produce as a result. You can always use these technologies to do that, regardless of what the idea is, regardless of what the opinion about what's happening is. Again, it has nothing to do with realities. It is all about the assumptions that you make. This means that when it comes to shale wells, these technologies have nothing to do with reality. They're all about assumptions. No matter what your boss or your manager likes to see, you can always use numerical reservoir simulation on RTA to show them that they are correct. They change their mind in a week, completely 180 degrees, and they let you know, and you can use exactly the same thing, make the assumptions different, and tell them that they are correct. While what was correct was exactly opposite of that only a week ago. For example, depending on what your manager or boss likes to see, you can prove using numerical reservoir simulation and RTA in the context of shale, not conventional modeling, but in context of shale, you can prove that long stage lengths are good, and then you can change it, say no, shorter stage length are better. Both of these can be possibly proved in the same asset, in the same number of wells, and given the same type of results that you have received. The number of cluster per stages could be smaller, could be larger. It all depends what you want to prove. The proppant concentration could be smaller or could be larger. It doesn't rely on the reality that happens. It relies on what you want to prove. And both cases is absolutely possible to prove and get a history match of what was happening in certain shale. It is time to overcome the speculative resistance to the required paradigm shift. And what I mean by that is a lot of people who have a traditional view of oil and gas industry and science in general, they resist incredibly when you want to use fact-based and purely data-driven approach to solve problems in our industry rather than using conventional physics-based modeling, mathematical equations. So it is time to overcome this resistance. It requires a paradigm shift, a completely different way of looking at things, and that's how you move to a purely data-driven and purely fact-based, not physics-based. Well, it's actually physics-based. The only difference is it is not equation-based. The physics based is based on your understanding of the physics and your knowledge of the physics and data knowledge fusion and not data and equation fusion. Uh, Here we scratch the surface of all that is possible in the application of petroleum data analytics to reservoir management and production operation of shale wells, what we have named as shale analytics. Here we demonstrate how the existing data collected from the development of shale assets can help in developing a better understanding of the nuances associated with the operating shale wells, how to learn to integrate the field experiences that you gain with the actual field measurements in order to optimize the future production and operation, and how to create a system of continuous learning from the data that it's generated on a regular basis. And by that, I mean that shale analytics allows you that every barrel of oil or every MCF of gas that is produced is not only bringing a return to an investment, but also it enriches our understanding and how of how shale needs to be treated in order to maximize the return on investment. That's how you will be able to analyze, model, and optimize what's happening in the shale wells. The major difference between shale analytics that we're going to cover in this course and conventional techniques, numerical reservoir simulation, rate transient analysis, and decline curve analysis, to analyze, model, and optimize production and recovery from shale is one major fact. In shale analytics, we make no assumption whatsoever. We make no simplification. We use hard data and reality in order to come to conclusion. Thank you very much. We continue in the next video, the rest of this introduction.